Hello everyone. We are going to start with characterization of invertible matrices. This is section 2-3 of matrix algebra for our book by Lay. So before I go into this section, I am going to recap some of the things we have done earlier. Now, we have learned about what is an invertible matrix. Now remember, invertible matrix is also called a non-singular matrix. So if I say that A is invertible, what I'm saying is that A times with A inverse is the same as A inverse times A equals the identity matrix. And very important to keep in mind is that we are going to be talking only of square matrices. Then we learned about some basic properties on invertible matrices, like if A is invertible, A inverse is also invertible. Then product of two invertible matrices are invertible. And then we talked about A transpose is also invertible. And then we also looked at if we are finding the determinant of a 2 by 2 matrix and its relationship to matrices. So we saw that if determinant of A is non-zero, it implies that A is invertible. A very, very important thing we will learn as we go. Okay, then also an invertible matrix is row equivalent to an identity matrix. And if we have that, we can find the inverse of the matrix by watching how the row reduction of A goes to I. It's simply if you're saying if A is row equivalent to I, then A comma identity is row equivalent to identity comma A inverse. Otherwise, if this is not happening, A will not have an inverse. And we also learned about in elementary matrices. An elementary matrix is one which is obtained by performing a single elementary row operation on an identity matrix. So these were some of the things we have done earlier. And in this section, we are going to be talking about two important concepts. One is the invertible matrix theorem. The other is the invertible linear transformations. So let's start with invertible matrix theorem. Now, invertible matrix theorem in a nutshell is nothing but concising everything we have learned so far in chapter 1 and also some things we did in section 2.1 and 2.2 of our book. So let's look at this very important theorem. This is called the invertible matrix theorem, and here we are only applying to a square matrix. So let's look at this. If A is a square n by n matrix, then the following statements are equivalent. That is, either all the statements are true or all the statements are false. Suppose we are looking at that A is an invertible matrix. That means it is row equivalent to an n cross n identity matrix. That just came from our previous section. Then A has n pivot positions. If A has n pivot positions, then also it says that this equation Ax equals 0 has only the trivial solution. If you guys recall, this is coming from our homogeneous equation, section 1.5 of the Lay book. And then the columns of A form a linearly independent set. If you look in terms of section 1.8 of the Lay book, the linear transformation x to Ax is 1 to 1. Then the equation Ax equal to b has at least one solution for each b in Rn. The columns of A span Rn. The linear transformation x to Ax maps Rn onto Rn. And this is basically the definition. There is, if A is invertible, then there is an n cross n matrix C such that C times A is identity. And also there is an n cross n matrix D such that the product of A with D is identity. And the very last statement, A transpose is an invertible matrix. So all these things, guys, we have done earlier. So these 12 statements are either true or either they're all false. Very important to remember that we are looking of square matrices when we apply this invertible matrix theorem. IMT is the terminology you'll be hearing me saying a lot. So let's look at some of these observations from this IMT. The very first thing is that every statement in this theorem describes a property of every n cross n invertible matrix. If you take the negation of the statements in this theorem, it describes a property of every n cross n singular matrix. Remember, I said that if I have an invertible matrix, that means I'm having a non-singular matrix. So the negation is basically matrices which are not invertible. That means matrices which are singular. For example, if I have a singular matrix of size n by n, and it is not row equivalent to the identity matrix, which simply says it does not have n pivot positions and it has linearly dependent columns. Let's look at an example of applying the IMT on a matrix. We have a 3 by 3 matrix over here, and we would like to know whether A is invertible. So we go back to our section 1-2 of the Lay's book, and we look at the matrix A. We apply, remember the row reduction algorithm? So we apply the algorithm, the row reduction algorithm, and we get that we have 3 pivot positions. So this is 3 pivot positions. When you apply this algorithm, clearly by IMT, this is invertible. Or we can think of it has 3 independent columns. Again, it is A is invertible. It's just basically you have to do the row reduction algorithm. Okay, so on this one, so as we said earlier, it has 3 pivot positions, hence invertible by the invertible matrix theorem statement 3. So here I'm actually using the numbers, so you can think of this as the statement number 3. Now keep in mind, we are always going to apply the invertible matrix to square matrices. And if you have a matrix, suppose we have a matrix of 4 by 3, and we find that it is linearly independent, but we cannot use the IMT to say, oh yes, if this matrix we have A by 4 by 3 is has independent columns, then if it is used in an equation AX equals to B, then it has some solutions. We got to be very, very careful. This is the key, guys. This is the most important thing. It only applies to square matrices. Now let's go ahead and do some examples from the book. And we are using the 5th edition. Let's start with the question number 11, which are true-false statements for us. Here it says, if this equation AX equal to 0 has only the trivial solution, then A is row equivalent to the n by n identity matrix. Now remember, we're talking of whether this is true or not. So we have to think back what kind of a matrix we have. We are having n cross n. Okay? And we're saying this equation has a trivial solution. Then it is row equivalent to it. So when we go back to our IMT, that means we are looking at number 4, statement number 4 and statement number 2. Statement number 4 says that this equation AX equal to 0 has only the trivial solution, then A is equivalent to the n cross n identity. So we're looking at these two guys. So in these two, if the number 4 statement is true, then this is also true. So we have got to be very careful. So the answer to that, first of all, is true. And it is, if there's some justification, the reason is if this statement is true, then automatically this statement is also true. So the answer is true. It says if the columns of A span Rn, then the columns are linearly independent. Clearly, if we look back at our statements, this is statement number 8 and this is statement number 5. So if statement number 8, clearly it is true, because if statement number 8 is true, then definitely statement number 5 is true. Let's go back over here. The columns of A span Rn. The columns of A form a linearly independent set. They are part of the whole IMT team. So clearly if 8 is true, 5 is true also. Now let's go back here to the number C. If A is an n cross n matrix, then this equation Ax equals B has at least one solution for each B in Rn. Now clearly this is one of these statements. We agree with that. This equation has at least one solution for each B in Rn. And I will say the answer is false. And you will say, why? The thing is, this statement can only be true if your A is an invertible matrix. An n cross n matrix does not imply that it is an invertible matrix. It is simply saying I have a matrix of size n by n. So very important that you have to read down every term in the sentence. So if A is an n cross n, then this equation is true. It is not, because IMT is talking about invertible matrix. Okay, so it's important how we are looking at the statements. Okay, let's look at the next two equations. It says, if this equation Ax equal to 0 has a non-trivial solution, then A has fewer than n pivot positions. And this is also true. The reason is because these are negation statements. Remember what the IMT says. Either all these statements are true or all these statements are false. So here we are saying that the statement says this equation has non-trivial solutions. That's what the statement is saying. Then if it has non-trivial solutions by IMT, it will have fewer than n pivot positions. That happens to be true. Okay, let's go and look at one more. If A transpose is not invertible, then A is not invertible. Very much it is true. Because remember, this is the negation. Remember, these statements is the negation of the IMT here. It says if not negation of IMT, like it says here, we're looking at the fact if A transpose is not invertible, that means if the is not invertible, so IMT is talking about the falseness over here. That means A is also not invertible. Okay, so very, very important that we are looking at these parts of it. Okay, now let's look at other questions from the book. It says, when is a square upper triangular matrix invertible? Justify your answers. Now remember, what is an upper triangular matrix? Upper triangular matrix is a matrix where all the entries below the diagonals are 0. So suppose we have 1, 2, 3 here. These terms are going to be 0. Suppose I'm just taking a 3 by 3. Remember, we're looking at a square upper triangular matrix. So I'm saying 1, 2, 3. I'm taking an example. Or we can have this to be 0 also. Why not make this to be 0? So 1, 1, it can be anything. It doesn't matter to us. What are these terms? So I'm just taking a 3 by 3. So this is an upper triangular matrix. Now, when do you think this is going to be invertible? For a square matrix. Now let's look at this example which I picked up. 1 star star 0 2 star 0 0 0. Now notice, according to IMT, first of all, it's a square matrix, right? But for it to be invertible, all the diagonal entries have to be, non-zero. If you remember that, remember we talked about diagonal matrices and its relationships. Or we can also think of that fact is that an invertible matrix has to be row equivalent to an identity matrix. So if this is already a row echelon form, for it to be invertible or it to be row equivalent to an identity matrix, it's very, very important that this part should be non-zero. So for the answer to this, as it is the upper triangular matrix, let's write it down. The upper triangular matrix is already in the echelon form. Okay, so for it to be invertible, it has to have non-zero diagonal entries. Okay, the reason is by IMT, every invertible matrix is row equivalent to the identity matrix, here IN. Okay. Now we're going to continue with later problems in the next videos. Thank you.